Okay. I've heard a couple questions outside of lecture. So when it comes to computing the view factors, let me just give you some ideas. So first of all, there's a situation where you have like a sphere and you're trying to compute the view factor. I give you the view factor for this library to be like a view factor between a sphere and, let's say, like a rectangular plate like this. But the sphere is over the corner, right? And you sort of wonder, how does that help me? So remember that trying to get the pieces to all kind of add up. So in this case, what you could do is you could take advantage of symmetry. All right, so this is a kind of a big hint for this homework. So I could compute the view factor for the quadrant here of a rectangle. I could also do view factors for similar quadrants like this. And together, all four of those quadrants, you add them all up, that's the total view factor from the sphere to this surface. So that can be one way that you maybe piece things together. So maybe that's the view factor from the sphere to the tube. From the sphere to the bigger surface, remember you can use like virtual surfaces. You can do the same thing. You can use the idea of adding things together. So like a view factor to this, you could maybe take a slice out of this view factor here and sort of subtract that off, and that would be the view factor to the bigger surface. Right, so that you don't have to have a library for everything. You can take advantage of symmetry, reciprocity. You can take advantage of adding things, subtracting things. Just keep in mind the overall energy balance idea, that the energy that you're accounting for sort of has to go somewhere, and it's going to add up. Okay, questions on that? No? Yeah? Is there a question? Okay. All right. So then today what we're going to talk about is blackbody radiation exchange. This is now, we've got to the point where maybe, hopefully we understand view factors a little bit. This is just the fraction of light that goes from one surface it's emitting to another surface. Now we're going to extend that into the energy realm and think about how you'd come up with a system of equations. This is like parts C, D, and so on in your homework. Okay, so blackbody radiation exchange. So first I want to recall the definition of emissive power. Emissive power. So this is E sub B. My blackbody emissive power is the integral from 0 to infinity of EB lambda d lambda, which we showed is also equal to sigma t to the fourth. If it so happens that the surface is not a black body, you might include some emissivity here. But for this problem, because it's a black body BB, we say emissivity is equal to 1. And this sort of goes away, right? It's implied, but it's not something that we have to specifically keep track of. So this is our definition of emissive blackbody power. So what we can do with this is note that we can rewrite our expression. I think I maybe got to this a little bit last time, but we can rewrite our rate equation for radiation as follows. So we would say Q dot from surface I to surface J is equal to the view factor, F, from surface I to surface J, times AI times, well, sigma Ti to the fourth minus sigma Tj to the fourth. All right, and there's a reason why I put the sigma Ti and sigma Tj, like I brought that sigma inside. And so you can identify the fact that what we have here inside the parentheses is my emissive power. Okay, so where we have this T to the fourth, we can actually rewrite this kind of in a more straightforward way as Fij Ai times the emissive power. So this would be EBI minus EBJ. All right, and we do this, and like usual, what we can see from this is that there's maybe an analogy with our circuit again. You have this potential, EBI minus EBJ, and then you have some resistance associated with it. Right, so we kind of got into this a little last time. But what you say here is this thing out front, this is 1 over RG from I to J. It's my resistance. But now I have this potential, the EBs. They sort of look like the temperature potential in a lot of the other rate equations that we've used. So I can think about this radiation as, instead of the difference of like temperature to the fourth, or sigma temperature to the fourth, think of it as a difference in emissive power. And once you've made that jump, now we can use a lot of the tricks that we used before for like resistance networks, and expressing things that way for radiation. We just have to do it in terms of EB instead of T. Okay? So with this, we would rewrite our equation Q dot Ij is equal to EBI minus EBJ divided by the geometric resistance RG from I to J. And to maybe give a picture to what we're saying here, we're saying we have some surface up here. Let's call this surface, this is surface, I. And we have another surface over here. This is surface J. And what I'm saying is that there's, for heat to flow from I to J, there's a resistance in between these. Right? This resistance we call our Gij, a geometric resistance. Units are 1 over meter squared. But then the potential, the driving potential between the surface I and surface J would be these the sort of nodal emissive power. So this would be EBI and EBJ. All right, and then we'd have some heat flow like this, and the heat flow we'd call, say, Qij, or if we happen to draw it the other way, which we could, we'd call that Q dot Ji. All right, one thing to point out is with that heat flow, Q dot Ij, that's going to be equal to minus Q dot Ji, which is equal to EBI minus EBJ over RGIJ. So turns out we can kind of write that heat transfer either way. We just have to be consistent with how we've drawn the arrow and the way that we relate the emissive powers. So like we're going from one temperature to another, here we're going from one emissive power to another, EBI to EBJ, in the direction that we drew it. So Q dot Ij is from I to J. We subtract J from I there. All right. So we can take this approach, and then from this we can start making more complicated setups, make more complicated problems, and then solve the system of equations. Where are we trying to go with this, right? We're basically saying, I know something about the geometry, the areas, I can compute the view factors, but what I don't know necessarily is this emissive power. Like I don't know maybe Q dot, and I don't know the temperature, i.e. the emissive power of the surface. So what I want to do is come up with a system of equations that lets me solve for Q dots and lets me solve for EBs, which then get me to temperature. Yeah, question?
So just to be clear, the RG, IJ, that's not thermal resistance, it's the geometric.
It's the geometry, yeah. The question is RG, IJ is the geometric resistance, which is defined as 1 over the view factor times the area. All right? Yeah.
And will we have like geometric resistances combined with thermal resistances?
Yeah, it's a really good question. Would you have the geometric and thermal resistances combined in a single network? No, you cannot combine a geometric resistance and a classical like conduction, thermal resistance, convection. You can't combine them because they have different units, right? They're different. What you'd need to do is figure out the energy going into a certain point. Let's say a certain surface, have a resistance network, say it's conduction, convection, whatever, that goes into that point, then the energy you would equate to the energy leaving in a different resistance network that has geometric ones with it. Right? Hopefully that'll become clearer later. Other questions on this?